Hey everyone, welcome to another episode of the Common Lisp Study Group. I'm your host Ram Vedam with Atlanta Functional Programming. Um, Today we're going to be discussing a different functional data structure library that I found for Common Lisp called Sycamore. There are a couple of these out there, and I wanted to kind of like compare and contrast some of them, their design decisions, some of their approaches and so forth, which is why, last week and last few weeks we covered the fsat library. This week we're going to be covering Sycamore. There's one more library that I attempted to try yesterday, but I will let you know the library name and will tell you that, long story short, for some reason it doesn't work on SBCL for Mac. It may work on Linux, but I have not yet went down that path. Before we begin, I thought I would first give you guys a little bit of a reasoning behind some of this exploration. Right now, I think, as I mentioned last week when we were covering last few weeks when we were covering the fsat library, that for the most part, while there is a functional API available in Common Lisp for the majority of the basic sequence data structures, a lot of the core data structures are by default more or less mutable, which makes some sorts of applications require a little bit more work if you're trying to do it in vanilla Common Lisp. Luckily, because of some of the features that are available in the Common Lisp library, mainly things like macros and the meta object protocol, a lot of the features that are needed in order for one to create these kinds of libraries is at their disposal. These features are at their disposal. Sycamore is another one of the libraries that is similar in design to fsat, but there are a couple of small but significant differences. One is some of the core data structures that are provided by the library. We will cover some of these today. But more importantly is, while for the most part the majority of the functional data structure libraries that are available in Sycamore are based on the same data structure design that fsat is based off of, and mainly, to give you an overview, both fsat and Sycamore use what's called a weighted balanced tree for a lot of their data implementations of their core data structures. There were two different decisions from the point of view of API design. And we'll see that a little bit more as I show you some code examples, but I just wanted to briefly mention it here that it'll become clear that fsat, from its outset, was trying to make a library that looked as seamless and has integrated with core Common Lisp than what Sycamore's design decisions were. But I think one of the things that Sycamore at least claims, and unfortunately I didn't have enough time to do benchmarks on this, because of some of the design decisions that they made that sort of broke API compatibility in a sense, and made their API look significantly different than fsat, they ended up gaining some speed improvements that ended up making, in some benchmarks, say that it is about maybe 30 to 50% faster than fsat. Unfortunately, this is numbers that I saw in their documentation that I'm mentioning it to you, but I have not yet been able to come up with an example that would clearly indicate that that is the case. So that is something that, as we go through some of these examples, if any of you have particular ideas or suggestions and so forth, feel free to pop in and throw up ideas, and we can come up with something. So let's begin. The first thing that I'm going to mention is just some core data structures that I thought were pretty interesting. Other than the same thing that fsat has in terms of trees, sets, and maps and so forth, mainly dictionaries. There is a data structure implementation of the rope data structure inside the the Sycamore library. So for those of you who aren't familiar with what ropes are, I encourage you to read, and I will, obviously put give you a brief explanation here. But if for details, I encourage you to read the Wikipedia article on the rope data structure shown at this Wikipedia address. But in a nutshell, ropes are one way of handling essentially string editing. It's particularly used in the application of text editing programs where you have a large string of text and you can actually take the data structure of that large string of text and compose that or break down that large string of text into a series of smaller strings that are stored in a tree-based format that allows uh, logarithmic insertions and deletions and concatenations as well. Um, this is particularly useful, again, like I said, in text editing because you will be editing, a lot of different areas of a particular text structure, but you may not necessarily know its offset if you're doing this in a random access way. So having some sort of weighted balanced tree approach to the actual text will be beneficial so that you could, jump around to different pieces of the text in an efficient manner. So that is the data structure that we're going to kind of begin with, just mainly because I think it's a pretty fun uh, data structure to start out with, just to get things started. So to use Sycamore rope data structure, you have to use Sycamore :rope. And you see the rest of the arguments. The rest of the arguments are basically strings that are essentially going to get concatenated behind the scenes into this data structure. So if we say hello, and then we say we've got a space here, and then we say, we have a data structure that's in a world here, right? It will convert the character and the quoted atoms into a single data structure that this will compile, but let's throw this into a REPL so we see what we get. You'll see that it will convert this into a full-blown hello rope data structure that contains a length of the entire string itself, obviously, the height of the tree, and the subtrees that it constructed out of this string. And you can see that here the subtrees are, the left subtree is another rope data structure itself. The right subtree is an atom that contains world. You can construct ropes actually not only this way. You can use normal lists as well as vectors or arrays the same way, and it will treat each of these all fundamentally the same. It'll construct the same exact data structure that if we just paste here, you'll see that it's the exact same structure as we saw before, as if we just passed it directly into the REPL. I mean, it's as if we passed in the original construction that we saw earlier. So here, just to give you kind of a complete notion here of this example, we can also use world here, and this is a slightly different than what we saw before. Here, the substring constructions shows that the left subtree is going to be hello, and the right subtree is going to be a different rope state structure. So this is just a different notion on that. If you have some sort of terminating condition, it will attempt to actually go in and construct that terminating condition first. Once the thing is constructed, and I'm gonna, obviously for example's sake, I'm going to go ahead and set one of these guys into a global in our package here. We'll call it hello, and we'll say that it's going to be hello. Okay. So once we have this rope data structure, what can we do with it, right? So you can actually do a couple things. Obviously, one is the first thing is you can convert it into a string, and for that you have a nice little convenience function. You can't use just with output to string and all that directly. There is a rope to string conversion function inside the API that will give you this ability to just take in our oops, did I just mess that up? We have messed that up. Character. Let me try something else here. Maybe this is. I tried it with this example yesterday night. I thought it would do the same thing here. Hello, colon, world is not of type. Oh, sorry. I'm dumb. That's me being stupid. Forgot to construct the actual sycamore rope. There we go. There we go. So you have this rope to string conversion. Obviously, you could rope write directly to a stream. So with that, you can use sycamore rope write, which takes in, instead of using this print statement that I showed you here, it'll take in the rope that you want to pass in. And the default, if you look here at the stream, is standard output. So you don't actually have to go in and say, like, stream is true. And it will go ahead and you may notice that there's this escape character string here, print escape. That is mainly because if you do have escape characters or carriage returns or things like this inside your string, and this is particularly in the case of text editing programs where you might take a block of text, okay, that contains a lot of new lines and other special characters. That escape keyword argument is the one that you would want to use to actually go and change that. I think by default it is set to nil. Just check this here. Sycamore actually escape. Oh, it's set to true. Okay, so it is set to true, not set to false. So let's see what happens when we run this. This is going to be the same thing. If we go in and take, for example, the rope write our sycamore rope of the list. Well, I'm just going to go ahead and do this. Hello, please, world. And we run it, you can see that it'll work on all standard data structures the same. You can also put in new line. I think it's what is it? It's new line for carriage return. Yes. So. So this is all well and good. Again, if you set, just for completion's sake, if we go ahead and set our, escape to be nil, what happens? It'll just print out. I think it's not clear when I do this again here. It'll just print out the not the string as is. It'll print it out as if it was in standard output. So that's just a brief thing about ropes. I thought it was would be pretty neat to at least start with that, just because many people who learn data structures, we start with strings and basic strings, and we talk about the different string concatenation operations. But in a lot of text editing applications and places where you are doing a lot of manipulation and you want to jump around to different portions of the text, the rope or chord data structure becomes a very handy data structure to have, just because you'll be able to quickly, in logarithmic time, jump to a particular portion of the text and actually go in and edit the text accordingly. Again, for more information about how splits work, because I'm not covering, we're not covering the data structure in detail here, but for splits and deletes and all that kind of stuff, I encourage you again to look at the rope data structure Wikipedia page. And for folks who are looking at it, just as a reminder, when you're looking at comparisons to choosing a data structure in terms of performance, okay, you have to look at the common case on how often you're doing certain things to choose one. So in many cases, although it might look like string actually fits, it might be the case that it might be better to use a more tree-like structure just merely because of the application that you're applying string editing to. So let's go back to some of the more traditional data structures that are inside the Sycamore library. I'm just briefly looking here. If there are any questions, for folks who do have questions, feel free to go ahead and post them on the chat, both in the live stream as well as in the Hangout, and I'll get to them whenever I see them. So, first things first, let's talk about sets. Sets inside Sycamore are the same in terms of the mathematical definition of sets that we were talking about when we were talking about fsat. However, to construct a set is slightly different with Sycamore, and that's going to show actually you exactly kind of the design decision that they made in terms of creating some of these operations. To begin with, whenever you're constructing any of the core data structures in Sycamore, and this is separate from rope. Rope is a separate, special data structure in my opinion, just because it's used for a special use case. But for more of the traditional ones that we are, tree maps, queues, they have essentially tree maps, queues, and sets available in their API. You need to provide some sort of comparison function to the actual constructor, so that it will use that function internally to make certain optimizations, whether it be keeping the tree in a sorted order or so forth. So to use this, we're going to have to first create a comparison function. Okay, you need this is what he calls an ordering function. If you guys are looking at the examples inside his documentation. So let's do that. Just very simple comparison comparator for constructing a set. And I'm going to just go ahead and use the one that's available inside the Sycamore README, just because it'll give you guys a way of referencing other pieces of information. All this guy is doing is it's going to take two values. If you want to go ahead and do a declare and say that they're both fixed nums, that's fine, but I'm not going to go ahead and do that. And all it's doing is just a basic, comparison, three-way comparison. 1 second, I have to get this down. There we go. And if it's less than, A is less than B, return -1. If it's greater than B, return 1. Otherwise, our default is going to be 0. Right? Simple comparison. Now, to construct a tree set of integers, we can just go ahead and use this in our construction of a tree set by passing it into the tree set constructor. Now, again, notice tree set takes in the comparator first, so we have to pass in compares first. And then the rest of the arguments are just all the arguments that you want to inject into the tree using this. So let's say that if we wanted to do, -1, 2, -10, 40, -7, and we want to construct this tree like this, right? Internally, if we actually go and look at the tree, hold on, sorry, go, there we go, example tree set. You will see that when the tree got constructed, it is maintaining a sorted order of the actual tree set itself, all right? And it's using this to keep it in essentially a vector. So that way you're able to do quick access to any particular location inside that vector using this simple string compare. Using this simple comparator operator. Now with this, you do have a couple of things. You do have insertions. Sycamore, tree, set, insert, right? Yeah, there we go. And we take in the example tree set, and let's say that we want to add 0 into the tree. All right. Now, if you look at the example tree set, you'll see that it has not been modified. This is another illustration of what I was saying earlier. This is a functional library. And so unless you actually, assign this to something, this insertion, it's just going to be a piece of garbage that's going to ultimately be collected. So let's actually go here, grab that, print it. You can see that the example tree insertion is, again, keeping it in sorted order. This is a really clear, clean thing that I want to show you. We also have basic removal. Again, and this is similar in terms of the API that you may recognize in terms of fsat's API. But again, implementation is just ever so slightly different. There are some subtleties there just to keep aware of this. Tree set removal, and you'll see that we can grab a set. Let's see here. Hello. Actually, we'll take the previous example. And let's say that we want to grab want to remove 2 from it. All right. You'll see now that it'll create a new tree set data structure, and with 0140 removed. Tree set provides all the basic operations: union, intersection, difference. Unlike the difference that we saw with, well, let's just go through it one at a time. Very quickly. Let's say that we have another operation, another example. Reset. Okay, and this guy is going to take our comparator, and we're going to have 1, 2, 3, 4, 5. All right, simple enough. If we go in and let me just go ahead and do this for folks. And just adding some of these so that we can add this to what's it, our GitHub repo for folks to use. Okay, cool. Now let's go ahead and do set operations. You know what? Instead of doing this, I'm gonna make this guy into a let form to make things a little bit examples. Okay. Let me just go ahead and do this here. Let A be 1, 2, 3, 4, 5. B be sycamore, reset, compare 0, 1, 2, 3. Okay. So now let's go ahead and do our basic tree set union, which takes in our 2 sets, and it'll give us the union. And let's do this. Let me do this. Make things a little bit even better. Format T union A. Okay. Format T intersection. Just so that we have a nice little labeling when we're reviewing this in the REPL. This is giving us our intersection. Thank you. A and B, and then we have also our set difference. Okay. Our set difference A minus B. I'm going to show you something a little bit interesting about the set difference first, before I run this particular piece of code. Sycamore set difference B. Okay, so let me grab these 2 guys, print them. Here we go. Okay. So here, what I wanted to show you straight up is sycamore tree set difference and B. To start off with here. Unlike fsat, where it has 2 different types of set difference operations. If you remember, there is one that's more traditional, that's more like this. They'll give you A minus B straight up. That is, it'll give you the elements that are in A that are not in B. But it had something called fsat set difference 2, which gave you both operations, which is a multiple value return that gave you both A minus B and B minus A, and depending upon what you wanted, you can ignore the other return value. Now, this for folks is not it should not be a big deal, because obviously as we did before, we could make our own multiple value return that did both. But I just am letting you know that this particular library does not have those kinds of similar operations that you are familiar with the fsat. And it was a distinct design decision, again, by the author of the library, mainly because I think in this particular case, there were some other operations that were more higher priority. But as you can see here with this operation that we have, all of the set difference and set unions and so forth are pretty much the same in terms of their mathematical definitions. There isn't much to really display and say, wow, this is really, really, really freaking awesome. But I just thought it would be particularly useful for folks to at least be aware that it is there. What's interesting about this library is it also provides mapping operations, but they're not generic in the sense that they are. I saw at least two different types of maps. There's a map treemap and a map treeset. We're going to talk about map treeset right now, just because we're dealing with sets right now. But I'm just mentioning it to you that you might. This is something that you might want to be aware of. Right. With the map operations, there we go. With the map operations, sycamore map tree set. What you could do is you can actually provide a result type of this. So let's say that we want a vector. Usually you want to use a vector because it's a continuous block of memory instead of a bunch of conses. You could take in an operation. Let's say that we're going to use 1 plus. All right, 1 plus is, if you recall, just taking in a number, and it's just going to go return the increment of a number. It's kind of like incf. And we could pass in our tree set. Let's go ahead and just simply create another tree set here. 1, 2, 3, and we map it. Whoops, did I mess something up? One plus should work, but okay, I'm doing the right thing here. Let me try incf. Oh, sorry, my apologies. This is not about this guy, it's about this. I forgot to add the comparator. Unknown result type, vector. Interesting. Hold on a second. What did I mess up here? I could use a vector here. Guess it can only work on lists right now. Shift. No worries. Let's do this. Interesting. So there's a bug here. I didn't try this vector thing example last night. So normally you can provide for a lot of these APIs either lists or vectors, but it looks like for map tree set they did not correctly implement the vector implementation. I will post a bug on the GitHub repository for this, and I'll go and look into that. One final thing that I wanted to show you, well, two more, but first we're going to talk about construction. Right now, so far, we were dealing with tree sets directly using this tree sets constructor here that we saw. There's also a sycamore make tree set with the compare operator. And this allows you to create essentially an empty set, right? So you see this. Let's go ahead and create a quick example with this. Now we can actually go ahead and do tree set empty. There is not an empty here. Interesting. Okay. I thought I saw an empty here. We could just simply use preset count. And then you can see that there's nothing in here. Again, just like what we saw before, we can insert into this just like normal. And we can only set it one item at a time. But, this is again a functional library, so if we go back to the example, it's going to be still set to 0. There are many other tree set functions, as you just saw, like when we're looking at trees, just like ropes. Ropes have, all these core data structures have their own relational operators. You can get sub ropes. You can, in the case of tree set, you have max, min, reference, find, list, remove, compare. A lot of stuff that you would normally be aware of that's part of the core standard common Lisp library, but he went ahead and made special versions of this so that he could add certain optimizations to it. So before you go and start writing your own versions of this inside of your use case, please go back and look at the API docs, particularly to see if there is a version of the particular operation that you're looking for. So, like for example, if you want a particular position, a particular value at a particular position inside a set, you can go and grab from the set, if you know the subscript, the location, the particular value inside of that tree, and then it will return it. So in this case, as you saw here, example tree set, our fourth value is going to be 2, just because we have 5 values in there, and it'll give you random access inside your particular tree set. I'm not going to go through all of them. There's just a lot. I think exploring this library a little bit more for yourself is useful. One final thing I will say that's available inside of the tree subset of Sycamore is the fact that you can convert this directly into a list. So, and we see that's particularly useful in some cases, especially if you want to leverage existing vanilla common Lisp API calls, and you want to then convert it back into a tree set inside a Sycamore. So that's tree sets for now. We're going to be covering tree maps, but I'm just going to stop briefly here and see if there are any questions. That way I could just get a drink of water here. Okay. I didn't expect any questions, just mainly because a lot of this stuff should be pretty obvious. I'm not showing anything specifically interesting. Before we move on to tree maps, There is one more particularly interesting thing that treesets has that I'm happy that's available that's in the library. That is, there is a reduction function. Just like we have a map function, there's a reduce function inside of uh, Sycamore for tree sets. All this guy is doing, let's say that we have our set Sycamore tree set compare 1, 2, 3, 4, 5. Okay. Inside here, we can unlike fsat, which uses reduce directly, and I think it created some set reduce operations where you have to convert it into mainly you have to convert the using I think either gmap or something to convert it into essentially a vanilla a common Lisp sequence object that will then allow you to do some reductions on it. Here we have two different types of folding operations. He's using fold. This is a big difference from many other libraries that we've seen in the past. A lot of libraries tend to stay within the common Lisp terminology. I've never seen any common Lisp libraries use fold unless they were inspired by, say, ML of some sort. But fold and reduce, you could think of fold and reduce as being essentially the same operation. It will take in a function. Let's say that we want to pass in. Do I have to write? Yeah. Let's say that we want to sum all these. Obviously we want to pass in add, which will take. It's a variadic argument, so we'll take all the arguments ahead of it, give it an initial value, and then we can pass in our set. And what it will do is you gotta remember to print it. It'll go ahead and run like any other reduction operation. Now you saw that there is also a similar reduction for tree maps, and we'll be going through that in a bit. But a lot of the API, as it stands today, deals with tree maps and tree sets directly. There is a third data structure that has they created for amortized for an amortized queue, but from the looks of it, this is a fairly new addition. It doesn't have a map operation. It doesn't have a reduction operation. So if you're doing anything with map or reduce, and you're trying to do transformations, especially using either tree map or tree set, if you're using Sycamore especially, would be a better approach, so that way you have some convenience functions that you don't have to go and write some calls yourself. Now, that said, if you want to go ahead and do that, go right ahead. I think pull requests are actually welcome on this project. The project is licensed under BSD, so you can do what you will with it as well. I'm just mentioning the BSD license, just particularly so that BSD 3 clause especially, just so folks who are on this stream that might be wondering if you can use this in a commercial project, you can certainly do so. This is something that is definitely useful for folks who are in that realm. So, example of an empty set. Let's talk about tree maps. Now, tree maps are just basically dictionaries. I think this is fairly obvious for folks who come from other languages. It is a proper dictionary. I'm going to go ahead and create an empty map here just to show that, just like before, we do have, the ability to make an empty tree map. Obviously, I'm just going to use the same comparison that we're doing before. We're just going to do a tree map of integers. I'm not going to deal with the key value pair piece right now. It's just so that we can keep things somewhat simple. Just pull up something here. Whoops. Okay, we can just get to it when we get to it. All right. So for this, if you go and look at the empty map structure, this is a tree map. I wanted to start with an empty tree map just to show you kind of the same thing that we saw before, mainly that it will it'll take in the comparison operation and then it'll create a root node. This is the same thing that we saw before because, again, going back to what I said in terms of all these data structures, almost all of them are implemented using weighted balance trees. I'm not entirely sure about the amortized queue, but I did confirm that at least with tree maps and tree sets that they are. And I think ropes are also implemented as weighted balance trees too as well. Folks who are looking at the README, please look at especially the Wikipedia page linked down there that will show you the implementation on how to implement the weighted balance trees. It is a very standard way of implementing various dynamic sets and dictionaries. Goes back to the actual 70s. And I remember actually seeing it in one of my very old data structure books that I have lying around. So folks who are interested in particularly implementing other types of data structures and wonder what might be a good implementation idea, especially if they are dynamic data structures, weighted balance binary trees are one way to go. They are a type of self-balancing BSTs, much like red, black, and AVL. They're in the same family, but red, black, and AVL have certain optimizations on them. For the rest of this coverage of tree maps, I'm just going to go ahead and create an example tree map here, just like I have an example tree set, and I'm going to use the tree map call directly. Did I mess up on tree? One second. My mini buffer doesn't seem to be giving me the okay, I'm assuming it's got to be the same. Let's see here. Minus 1. 100 minus 2. Plus 4. 55 and 6. Do that. What are we going to do? Sycamores tree map is undefined. What are you talking about? I see it in the API. Did I mess that up? Come on. Interesting. So it looks like the only way to create tree maps, I thought I could actually pre-populate this guy, but it doesn't look like I can. It's kind of weird. But that is going to be... alright. That's fine. To insert into this guy, we can use our standard tree map insert. Tree map insert say example map. Now, you may be wondering, well, what is this comparison function that's being happened in this empty map? Compare is only for comparing keys inside of the map structure. It has nothing to do with the actual values themselves. It is making sure that the indexes are sorted. So when you're trying to do quick access to a particular key, you can certainly do so. As far as I can tell, when I was playing around with this library, I don't think there's anything that is conveniently made for values. But you know, I'm still exploring this library. I have not seen anything around that that type. But I'm just letting you know for folks who are tuning in, just wondering, well, what does this provide us, right? So here we could just say 0A. We'll go ahead and what? Oops, sorry, my mistake. Let me go and change that. Oops. There we go. Shift G, clear. There we go. Let's go ahead and make this tree map into this empty map here into example tree map. Okay. So let's do this again. Sycamore tree map insert example tree map. 0A. Internally, when tree maps are being constructed, they're going to go ahead and make them as dotted pairs. They're almost all dotted pairs. So the car is going to be the key. The cutter is going to be the or rest is going to be the actual value of the data structure. What's hold on a second. There we go. Again, just like what we saw before, for some reason my REPL kind of messed up once. There we go. There we go. Just like before, our example tree map, when we did this insert, didn't actually get changed. It's a immutable data structure here. All right. I know I'm reiterating this because it's a functional library, but for folks who are used to using other data structure libraries, and I know it's the same with fsat too, a lot of times they will accidentally do like set f, or even they accidentally just call straight up insert, expecting it to be inserted into the data structure, not recognizing the fact that the data structure itself is a brand new data structure instance. It just copied all the old values into that data structure, or if they're doing some sort of shared logic behind the scenes, it constructed a new pointer to the new construction with this additional operation. And that is, you have to unlearn some of that when you're dealing with some of these immutable data structures, just so that you're aware that every time you're doing this, there's going to be, unless there are certain optimizations that are documented in the library, you're going to be dealing with almost always the immutable version of the data structure. So you're almost always going to be dealing with one copy of the original one if you're not doing anything else to manage those changes. So, and we can add a couple more into this guy. Let's go ahead and add, just for completeness sake, let's do this. 1E sycamore tree map insert 2C. So we have a couple of them, all right? So now, if we wanted to, and let me just go ahead and set this as a parameter here, called populated map. So now we have a populated map of these values here. So what can we do with this? You have, just like what we saw before, a map operator and so forth, but I'm just going to go through some of the accesses that are available inside of treemap. One is what we saw before, which was treemap count. And this is just going to give us the number of key value pairs that are inside of the map. You use this to essentially do what I was trying to do. There is no empty operation as far as I can tell for tree maps and tree sets. So you're going to have to look at the count of tree maps and tree sets in order to determine whether or not the map is empty or not. There's also, in terms of tree map, a way of getting all the keys and the values. Again, this is mainly you can see right now that the way it is currently structured, it's going to return it in reverse order. I'm not entirely sure why it's in reverse order instead of sorted order, ascending order. I have a feeling it has something to do with the fact that the root of the tree is what's determining how they're converting the actual how they're traversing the tree. I think it's how based on the traversal algorithm that the return values of the keys are that way. Same thing with tree map values. It's giving it to you in the reverse order of what you would expect. It's not first in, first out. As you can we added 0 first and 1 and 2, but instead it's the other way around. There's other interesting things about the tree map here. If we could just quickly cover some of these. One is, and of course, you have find here. I'm going to just cover find and contains here. Find actually takes in a tree map and a value, let's say our key, and it will go in and give you a multiple value return. It will tell you the first value is the value itself, the second one is the key, and the third one is whether or not it actually found it or not. So this is particularly important for those of you who are writing like destructuring bind like forms to know the order in which it's, or a multiple value bind form to knowing the order of which it's being returned. So if we do this, you can see that nothing. We looked for a key 3, so obviously the key is always going to be populated in the return set. But none of the values are actually. We didn't find a value, so that's why the first return value is nil. And we didn't actually find something in the data structure, which is why the third return value is nil. All right. So since there's no value associated with this key, the first return value won't have anything of the multiple return values. And because we couldn't find anything, the flag that'll tell you whether or not something was found is also set to that. Of course, when you're dealing with this in your multiple value finds, you can certainly use the last flag first before checking the first two. So those are things that you may want to just keep in mind when you're going through it. Additionally, instead of doing that, if you just want to know if it contains a particular key, you can certainly just use contains. So this will give you just straight up nil or false, or nil or true, whether or not a key is inside of the data structure or not. Then treemap also has this treemap hash table. All right. Treemap hash table will convert a populated map, if I remember correctly, into a proper hash table, and it uses the same default arguments of constructing the hash table. So you'll use it. You'll create a hash table with an EQL test rather than an equal test. I uh, I For folks who aren't familiar with the differences, I encourage you to go look at the hyperspec for a more detailed explanation of the different equalities, EQ, EQL, and equal. I think I'm missing one too. EQ, EQL, equal. Well, I think I got them all. And their differences. Hyperspec has a far better explanation of some of those than I do, so I can't. I'm going to defer to that that documentation. What else did I want to show about tree maps? Tree map keys, finds, contains, hash table. Hash table. Yeah, tree map insert hash table. So, tree map insert hash table takes in an existing hash table and an existing tree map and essentially converts whatever's in the tree map into the hash table directly. So what we saw before, we just pass this again to the previous one. It essentially took the hash table. Sorry, it took the hash table and converted it back into a tree map. So the conversion that you saw there is if you wanted to go to a hash table, you have to start with a populated map, and we'll just create a new instance of the hash table. If you want to go from a hash table into a tree map, so you could do some sort of operations on it using Sycamore, you could certainly do so by just simply using treemap insert hash table, and it'll go ahead and construct the object for you directly without any additional code. You don't have to go and manually do like a map hash and try to insert it into it. Although you can do so if you want to see what the performance differences are. What's this? So there's one function in this that in this library because we've talked about tree maps and tree sets, and I'm going to touch base on the mapping operations, and I think there's a fold operation too inside for tree maps too as well. There's one thing that I wanted to mention that's directly part of the library, but I could not think of an example for it, I'll be honest, but I'm just letting you know that it's available. So for some of these collection classes, Sycamore provides a macro for doing short circuit evaluations of arguments. He calls it OR compare. I'm not entirely sure if the comparisons that he's talking about in the documentation is related to passing in essentially the different comparison operators if you want to essentially have or compare use. So I'm not entirely sure if or compare takes in a different set of operations and then returns. Okay. It looks like it returns essentially a composition of those operations. This is my understanding of the documentation. I'm just briefly mentioning this to you just because I'm not entirely sure how to use this, but my guess is you'd want to use this if you want a more complicated comparison operator for insertions, removals, and deletions and sorting operations for either tree maps or tree sets. And you already, you want to break those down into their own separate functions and then do a composition of all of them so that way you can do a right to left evaluation of those and short circuit for the first one that is non-zero. Honestly, I haven't found a use for it yet, and I was playing around with this this week, but I'm mentioning it here just so that for folks who are wondering if there are composition operators to take multiple comparisons, there is one available to you at your disposal. Okay, let's talk about Sycamore map, tree map. Map tree map takes in essentially uh, 4 arguments. This is a slightly different thing um, than tree set, and this is why I think it bared some explanation here. So there are 4 arguments. You may notice in my mini buffer. Those of you who can't see my mini buffer, I encourage you to go to the documentation. I've tried my best to kind of blow that up, but I can't seem to figure out in the Emacs how to set that up. But map treemap takes in an order argument, a result type, a function, and a treemap. What is order? Well, when you're traversing a tree, there are many different types of traversals, right? Everyone knows this from who has taken data structures. There's a pre-order traversal, a post-order traversal, in order. Technically, there's also a level order, but it doesn't look like they have level order supported in the library. And you need to be able to specify, depending upon the ordering, you might get potentially different results. So you need to be able to specify the traversal operation in order to get the expected result that you want. So for this, the order argument inside map treemap is a keyword argument. I'm going to just show you in order, but I will go and briefly, show you, just for documentation's sake, that the first order, the argument is in order, pre-order, post order. And those keyword arguments do not have a dash in them. This is a very important thing to be aware of. We're just going to go ahead and cover in order right now, just because I think that's fine for this. We're going to take our result type again. After the vector thing, I'm not entirely sure vectors actually are being covered in this library, so I'm just going to go ahead and return a list. Pass in, again, our standard increment operator. This guy is, if I'm not mistaken, working on the... Actually, I think it gives me the key and the value. We're just going to go ahead and map this guy and print T key A value A KV, right? And we're going to go ahead and say populated map. And you can see here that all it did was it traverses the tree map in the order that you expected it to, using the traversal order you provided, and it will print out those values. Now, just to show you the differences, this is of type binary tree. Okay, that's interesting. That's really weird. My understanding was that you would actually... My apologies. When I played this out, it looked like it was working for my example on this, but it's not of type sycamore binary tree. It looks like I have to convert this into a binary tree of some sort in order for me to use pre-order, post-order, but the default is set to in order, and that seems to work. Let me go ahead and see why that's the case, if you guys bear in for a minute. Bear with me for just a minute. There wasn't anything that I had to do to convert that, did I? I don't see anything in here. The API. Undefined function. It looks like they changed something here in this library than the one that I did in the GitHub. That's fine. That's okay. Okay, I'm gonna make a note of this just because this is kind of interesting. Why it wouldn't allow me to do this. One thing that I'm going to mention though before we move on is that result type could actually technically be also nil in this map treemap function, versus in map treeset where the result type has to be something, usually a list. The three types, it could either be nil or a list actually for map treemap. So this is particularly useful if you want to go in and apply a transformation on every value inside of the structure. You don't necessarily need to do any sort of additional work on top of that, and you want to return those values. And the reason for this is if you look at this example here, we don't necessarily need the value, right? So why are we returning this? We could just say nil, and boom, it will go ahead, and this is as if we are traversing every option in the tree, and it's like a normal for loop for folks who would write it like a do list or something like that to grab every value from this. Okay, so let's talk about another data structure that is inside of this. And that is, actually, let me stop here for just a minute. Are there questions from folks in the audience? Okay. Let's see something here. I want to do. So one thing I wanted to take a little bit of a tangent on, and I was kind of waiting until we covered both tree maps and tree sets. I'm just going ahead and pasting this guy here just for folks who want to look at it. Result type. Okay. That. Okay. One thing that I was kind of holding off on until we covered both tree maps and tree sets is the fact that although this is a functional library, there are operations for folks who want to write stuff in a sequential manner. And they do macros, if I'm not mistaken, these are macros. Yeah, the do tree set macro and the do tree map macro. If we look at do tree, let's go ahead and use do tree set for example. Do tree set. This guy takes in a variable. Let's call it x. A set. Let's say that it's our example tree set. And you can provide an optional result. This is standard, even if you use, like, say, do list. Do list has an optional result object too as well. So it's using the same sort of form that do list has. For now, since I'm just doing a simple traversal, I'm just going to go ahead and print this, right? And all this is doing is it will actually go through and traverse through the list sequentially. If we expand this, this is nothing more than taking this do tree set, although it looks like it's actually doing things sequentially in the same way that do list does. Do list is very, very different. Folks who remember do list, I can actually, for completeness sake, let me go ahead and show you the differences. X list 1, 2, 5 print x. Okay. this is the expansion of that and the expansion of this. So as you can see, when we're doing do list actually converts itself into a block tagline block, which is typical of a lot of traversals. It's actually trying to get itself as close to um, the the code that you normally see in assembly. But in the case of do tree map and do tree set, they actually are nothing more than conveniences to taking your your function that you pass into the block, converting it into an anonymous function using flat, and then calling map tree set on it with the nil argument passed to it. So it's I don't see it being any performance. There's any performance difference. It's just a convenience for folks who just were like, okay, you know what? I just want all my instead of writing like a lambda, um, or even a named function. If there was a way for me to ultimately take a block of code and have the compiler go in and assign it into its own anonymous block, that would be ideal. Do tree set and do tree map will do that for you, which I thought was pretty nice, just because from a syntax standpoint, although I would like to use map tree set just in general from the standpoint of it all the time, it's just having the related operations. If you're especially using multiple sequential for expressions to evaluate a particular value that's coming through as you traverse through a set, is having that in one place is obviously useful. So since this does that transformation for you, I'm basically saying that you can use either do tree set and do tree map, or their map equivalents, and they're fundamentally the same thing. They're functionally the same thing for traversal. So, and it's the same with do tree map. I'm just gonna, for completeness sake, show you new example tree map. I don't think there's any values in this right now, just because I did not provide anything. Let me set a couple things in here. I'll write a much more crazier thing to populate this tree map and then check it in. So for folks who want to just see some dummy data being posted in there, just add one guy in here. Example tree map, and let's. I don't encourage you doing this. I'm just doing this for example's sake. Because this essentially is throwing away the temporary empty map, and making it a garbage. Let's go ahead and now run this guy. This here, what? There we go. I have to write it that way. Print K, do this, print T, E, E. All right. Now, the one thing to note about do tree map is, you saw before when we were attempting to use in order and switching between in order and pre-order, that there was an issue with the fact that it was expecting a binary tree being there. It looks like that that there's a couple of API things that are not properly exposed for converting a tree map into appropriate, binary tree, so that you can actually leverage post-order and pre-order traversals. It may not have been implemented yet, so honestly, I can't really tell right now. I have to go and look at the source code and see what's going on there. But it also shows here because of the fact that if do treemap was a direct, wrapper around the actual map function itself, it should have provided you some ability to actually provide the order, and it looks like it does not. So if you look at this thing, it just takes the key value, the map, and the optional result. And when we expand it, it actually does what we were doing before. It does map tree map in order. It doesn't return the actual value. That's why it's passed in nil. And then it took our block, converted it into a lambda, and then applies it to our tree map. So that's tree maps, sets, and ropes. One more thing that I wanted to touch base on very briefly, just because I haven't had a chance to play around with this data structure, is Sycamore provides a amortized queue. Now, folks who are not familiar with amortized queues, it's just another realization of the queue data structure, but it is something that I'm going to at least mention here. Amortized queue, at least its description, it is provided in the awesome book, and it's actually one of the references that the author used to actually implement this library. Purely Functional Data Structures by Chris Okazaki. In there, he talks about specifically amortized analysis, and the fact that since you're dealing with functions that are dealing with immutable data, they're just transformations. Okay. When you're trying to do modifications and such, you're ultimately creating a copy of this information. Unless, obviously the implementations could do some sort of shared structure so that it maintains the illusion that you're creating a copy of a new thing, but behind the scenes it tries to do some sort of shared structure to make sure things are fast enough. But because of this, what you're looking for is not a worst case performance analysis. You can't actually do that kind of analysis if it doesn't show the real intentions of a particular algorithm and the particular performance characteristics of a particular algorithm. What you're going to have to do is you're going to have to look over time and see the overall performance, the average performance of it across most of the common cases that you are dealing with. So with that in mind, there are a few data structures that are provided in that book, and I don't think all the data structures that are provided in that book are actually implemented in Sycamore, but it looks like it is a goal for this library to actually go and do so. There are other references in this one, but the one specific one that I'm covering right now is just mainly amortized queues. So you can treat an amortized queue as a normal queue. So there are functions for on-queuing items, dequeuing items, checking to see if we have an empty queue. So to start off with, we can create an empty amortized queue. We can create an amortized queue by simply calling sycamore make amortized queue. And notice it doesn't actually take any arguments. That's because you cannot actually, this is not a buffered queue, right? There's no buffer that that you're creating. It is a dynamically built queue, all right? So folks who are thinking that you might be able to do some sort of pre-allocation magic here, I'm sorry to say that this is not that's not going to happen. Once you have this amortized queue, and I'm not entirely sure if it's part of the core API, but right now the current API as it stands does not have the ability to create a buffer. But once you have a queue, you can actually do things like check to see if the queue is empty. Right? Is queue empty? Obviously, in this case, it's going to be empty. But to do that, you just need to call amortized queue MTP, just like every other. It's a predicate. It takes in the queue. There we go, and will return whether or not it's empty or not. To add things to the amortized queue, you're going to have to use onQueue and you're going to have to use onQueue, right? Or there's also a push version of this. So if you look at the difference, if I'm not mistaken, the push actually makes this implementation be treated like a stack. Interesting. Then what does onQueue do? If it's going to push it onto the front of the queue. It's not found in the sycamore package. What? I guess. Oh, my apologies. Not amortized queue onQueue is amortized onQueue. Thank you. This makes it sound like the onQueue operation creates a new queue, but the push operation doesn't. So now I'm curious. Let's see what happens if we use this guy. Print sycamore amortized queue push Q1. This should be empty. All right. Let's go ahead and do. So in both cases, it actually returns a new queue, but it looks like the documentation is giving a false impression that push is a destructive operation. But I kind of figured that it should do that might be just a typo, but better to be safe than sorry. So here's the difference between onQueue and push, right? And I kind of figured what that is. To begin with, let me first talk about the structure, just to give you some sort of idea on what the structure is. So amortized queues has a pointer to both the front of a list and the back of its list, and that's associated with reverse and forward. All right. When you're onqueuing something, you are normally trying to do first in, first out semantics. Okay. So you're actually pushing stuff into the back of the queue versus actually just so that it's like what you would normally do when you're onqueuing when you're in an actual queue in a line inside of like a supermarket or something like that. You're always at the end of the line, so you're pushing in the back of the line. To illustrate this, amortized queue is using the reverse iterator tag when you're using onQueue. But if you're pushing something, and this is kind of the same thing, like if you're in a queue in the store, and an individual is trying to push himself to the front of the line, he'll go to the top of the line and stick himself in there, and he's now at the front of the line. That's illustrated here if you're using the forward iterator. Now, what I didn't see in the API, and I'm guessing it's because it's probably not, it doesn't have like a doc string or something like that, is like a thing like pop. I think at the end of the day, whether you push or you onQueue to get out of the list, you're almost always dequeuing yourself, in which case you are going to go ahead and do this. Let me go ahead and set one of these guys up just for a simple example. Again, I don't encourage this, but better to be, for illustrative purposes, it's a better way of working things out. So if we do this, we've actually went ahead and populated it with the reverse iterator now. If we go ahead and dequeue our list, notice dequeue doesn't like tell you how many items that you can pop off. It only pop one off. It's going to go ahead and, oh, sorry, typo. It's just going to go ahead and pop off from the front of the list. Now, if we did a push, all right, just, you know, it's going to be the same thing. So if we do this instead, setf q, and then we populate this, all right? So this guy is setf, and then we did it. Q, forward 1, 1, reverse 1. Oh. Ooh, sorry. There we go. Okay, so I apologize. When I did the first amortized DQ, I forgot that that Q again is immutable, so it'll still have a reverse function 1. So we pushed onto the list this Q, just forward iteration of this Q, right? And we're trying to see what happens when you're actually going through it. The order in which that this is going to go through is amortized Q will actually pop off everything that's in the forward part of the list, all right? And it's keeping track of 2 lists for some reason. I don't know. I'm not entirely sure why about that. I have to go and look into the Okazaki book just to be aware of some more of the details. This is kind of the first time I'm actually seeing this implemented. I haven't had a chance to implement this myself. But and it's been a while since I've actually reviewed Okazaki. But the idea is it's keeping track of these 2 lists, and as it's actually dequeuing them, one of the 2 lists is getting emptied, right? And the order in which it's going to do it is because a queue is first in, first out, is it's always going to empty out the forward list, and then later on it's going to empty out the reverse list. So if we do this, as you can see here, the forward list is completely emptied. Now if we do this one more time, you'll see that the reverse list is also emptied. This is the same thing if you do, let's do a very quick example of this to really drive this home. We're just going to use onQ, for example, okay, just to make things a little bit easier. I'm going to go overhead and, again, use our good friend, this guy, the setf idea. So I'm making a lot of garbage here, because when you're doing setf here and you're using, and it's creating a new instance every time, this is going to be creating a lot of garbage in your Lisp image, but you know, this is fine. So what I'll do is do this, do list, do times, I say we inserted 10 things into the queue, all right? So now our queue has 10 things, all right? Just to illustrate this guy, I'm going to go ahead and do this as well. I'm going to to go and do times I10. We're going to dequeue it, and then I'm going to print the queue so that we could see the queue as it's getting emptied. All right. Clear my REPL so that we can actually see all this in a single slot. So the first time that we moved, okay, what happens is everything that is not if you recall let me share this again and do this. This is probably better. Let me do this one more time. Clear. This is our populated queue, just to keep things in mind. All right. Notice the ordering that the reverse iteration is. All right. The first time that we're actually going through and actually popping things off, okay, we dequeue the first things. Everything gets moved into the order in which it's going to be removed from the reverse iterator into the forward list. All right. And then the rest of the algorithm is just using the forward list. Because the forward list is what you pop off every now and then. And it's maintaining this reverse order, and I'm still not entirely sure why. I think it's really related to how the structure is supposed to be designed and based on the description of an amortized queue. It's because of this design that you will end up having this two iterations and two different lists available. Now, for those of you who are thinking that, well, shit, this looks like a copy for every operation inside of the data structure, it actually is just a pointer location that's being moved over. The actual value contents is not constructing a new instance of the object and doing an insert. It's sharing the structure, and it's just merely taking the pointer and moving and actually inserting it into the forward list. So space-wise, it's still, I think, constant space. It's still going to be the size. It's going to be the size of the list that the queue that was originally inserted into the queue, right? But once you have this, really you're just doing a pop and a set, right? You're constructing a new object with the cutter of that list, and you're popping off the value when you're dequeuing. That's at the front of the list, the car of the list. So here you can see that we are actually going ahead and doing that. We're creating a new, essentially, instance of the amortized queue, and then we're just returning it with the rest of the list that has not been emptied until obviously we empty it out. There are some things that I want to also briefly mention here. I'm going to go ahead and create this list again. So we have our populated queue. Let's say that we want to do some operations on it using some list operations that are part of standard common Lisp. You have the ability to convert using sycamore amortized queue list. All right, the queue, and we'll convert it into the list in the order in which it was expected. All right, first in, first out, and then you can use your standard Lisp operation to do stuff. Obviously, a lot of times you're using queues to essentially do scheduling and stuff like this, so it might be easier to just go ahead and I'll use the structure as is. I'm not certain. I would think that it would be better to go ahead and use that accordingly. But if there are operations that you want to do that, vanilla common Lisp has a really fast version of doing stuff, and you want to apply to every element in the list, you could certainly do so. And then do like what I was suggesting before with map treesat. You can actually convert out to the vanilla common Lisp, do whatever you want to do in vanilla common Lisp, serialize it back in, and do whatever you want to do it inside Sycamore, and then that would be fine. I think I covered all I wanted to do for this. Just double checking. I don't think I can do... looks like I can do this. It's one weird annoyance I've had with this library is the fact that some data structures don't have some pre-populations, others do. So I can never really be sure. We saw that with treemap. Treemap, I forgot, did not have a way of actually creating a populated treemap, which is weird. But it looks like amortize does. You can actually go ahead and do 1, 2, 3, and it'll construct a new list with the forward using amortize queue push instead of amortize queue on queue. Sorry, instead of amortize on queue to actually go and construct a new object that's pre-populated. So that's it for Sycamore. Again, these are purely functional data structures that are inside Sycamore. A lot of it are essentially realizations of data structures that are available in various papers, particularly purely functional data structures by Chris Okazaki. It also implements the ropes data structure that we saw that came out of a paper that was written in '95 by Hans Bohm. And it has some optimizations for functional sets. The references that you may want in order to look at some of the designs of the interfaces are available on the Sycamore README. I will go ahead and post a README inside the YouTube links for folks who want to see. I already posted for folks who are interested the GitHub URL. That GitHub URL, the README is at the very bottom of that URL, has all the information. Next week, we will be covering the... Actually, wait, let me just make sure. Yeah, next week. So next week, this is going to be a little bit of an off week just because I have another appointment. We will reconvene the week after on the 20th. There, I will be covering the Lisp interface library, which is another data structure library, but it's a different. It has a different style of design than the ones that we have covered so far, fsat and sycamore specifically, and I'm hoping also to cover in the coming weeks CL containers. One final note that I want to mention. Some of you who may be wondering where some of these data structures are, libraries, this list that I'm getting is coming from. There's an awesome list of pretty well-documented libraries available on Cody Reichardt's awesome CL GitHub repository, and it's been fairly well maintained. It has everything from build systems to different types of compilers and code generators to different ORMs and stuff. I'm giving a big shout out to this because this is a very nice, well-maintained little list that I'm hoping will continue to be this way. Folks who I will post in the YouTube links also this URL just so that for folks who are interested in looking at some of the other libraries that are available here to do so. As usual, folks who want to, who are interested in giving talks or have talk topics, feel free to post either in the YouTube comments or ping me on the Lisp Discord server or even the Functional Programming Slack channel in the Lisp chat room because I hang out in there. I will try and put your talk topics in the list of things to talk about. So until 2 weeks from now, I will see you guys later. I appreciate you all for joining me today.